In the previous lecture, we have discussed about the delta network and how it is converted into a star network to simplify the circuit and calculate the equivalent resistance. Here again we are here we have again a problem which is shown in the figure. We have to find the resistance equivalent resistance between A and B. Now as is shown in the figure, we can convert this delta network into a star network by using that rules, and we have converted it into a star network, and the value of resistance is R by 3, R by 3 and R by 3 after converting into a star network. Again this is also a data network, so it can also be converted into a star network. So here we are converting it into a star network, and the final diagram will be like this circuit diagram. So now this again will be R by 3, R by 3 and R by 3. Now in this diagram we see that these three are in series, and these are in parallel. Again these are in series, so we get the equivalent resistance, which comes out to be 5 R by 3, and equivalent of this will come out to be 2 R by 3. Again this is in parallel, so calculate using parallel formula, and the equivalent resistance will be in series with these two. So here is the value of after solving. Now these three are in series, so we can get the R equivalent of these here we see that these are in parallel, so we have converted we have got its equivalent equivalent resistance value, which is given by 10 R by 21. Now these are in series, so we can calculate the R equivalent between A and B, and that will be RAB equal to R by 3 plus 10 R by 21 equals to 14 R by 10, 14 R by 10 plus 10 R by 21, 24 R by 21 answer. Next I am going to talk about Kirchhoff's rule or law. To discuss this rule and law, we first we have some point to be noted. Some definition we should know about some topics. For example, node or junction. What is node or junction? A junction in a circuit is a point where there are more conductors, 3 or more conductors meet. Junctions are also called nodes or branch points. That is node or junction or branch points are a point where 3 and more conductors meets. For example, in this case here, this point is a node where 1, 2, 3, 4 conductors are meeting. So at least 3 conductor minimum resistance or conductor should be 3, and maximum may be any numbers of. Now loop or mesh. A closed circuit in the electrical network is called loop or mesh. That is it should be a closed. For your figure, in this figure, this is a loop. This circuit also represent a loop. This circuit also represent a loop, and this whole circuit also represent a loop. That is, in this diagram there are 3 loops. This is 1, this is 2, and this whole is also can be considered as a loop. So loop is a closed circuit, or it is also known as mesh. Now Kirchhoff's junction rule or Kirchhoff's current rule, KCL, it is known as KCL, junction rule or Kirchhoff's current rule, both are same, and it is, in short, it is known as KCL. The algebraic sum of the current into any junction is 0. That is sigma junction I equals to 0. For example, here this is a point O where many current are meeting and coming out of. Then the algebraic sum of all these currents should be 0. Now we take some sign convention here. If current is going toward the point or meeting at the point, then that current is taken as positive, and if current is coming out of the point or coming going away from the point, then that point is taken as negative. That is directed toward point will be positive, current directed towards the point will be positive, and current directed away from the point will be negative. Here it is shown. For example, at point O, many currents are meeting and coming out. So here I1 and I2 is directed, that is I1 is going in this direction toward the O direction, and I2 is also going towards O. So this I1 and I2 will be positive. Now at this point I3 is coming out from O, and coming out from I4 is also coming out from O, that is away from the point O, going away from the point O. So this will be negative. Now from the junction rule, these all currents should be sum of these all currents should be 0. So at O, because this is positive, so I1 plus I2 plus minus of I3 plus minus of I4 should be equal to 0, or this equals to I1 plus I2 equal to I3 plus I4. This law can also be written as the sum of here we see that I1 plus I2 minus I3 plus I4 equal to 0, I1 plus I2 equal to I3 plus I4. This law can also be written as the sum of all currents directed toward a point in a circuit is equal to the sum of all the current directed away from that point. The junction rule is based on the conservation of electricity. That is, this rule is based on conservation of charge. That is now we should know the Kirchhoff's loop rule or Kirchhoff's voltage rule, KVL. It is in shortcut known as KVL. Kirchhoff's loop rule or Kirchhoff's voltage rule, both are same, KVL, and in short it is known as KVL. The algebraic sum of the potential difference in any loop, including those associated MFs, EMFs, and those of resistive elements, must equal to 0. That is sigma delta V closed loop equals to 0. That is in if we are given a circuit, closed circuit, then algebraic sum for all potential difference about all elements should be 0. Now some rules are to follow how we can take potential difference, value of potential. For it we have to know the rules so that there should be no confusion in taking the direction of potential or EMF, how they will be positive and how they will be negative, where it will be negative and where it will be positive. If we follow these rules, then it will be easy to apply this Kirchhoff's loop rule or KVL. For example, for the rules for potential difference, we know that potential difference, final potential minus initial potential, that is delta V is equal to Vf minus Vi. Now if delta V is equals to positive, delta V will be, that the potential difference will be positive if final potential is greater than initial potential, and delta V will be negative if final potential, that is Vf, is less than Vi, that is final potential is smaller than initial potential. Now we have to take this concept, that is higher minus lower is positive and lower minus higher is negative. This is the general case. We know that if we subtract lower value from a higher value, it comes out to be positive, and if we subtract higher value from a lower value, then it comes out to be negative. So this rule also we have to see. Now positive terminal of a cell is at higher potential and negative terminals at lower potential independent of the current direction. It is this rule is in a circuit, closed circuit, or in any loop. If they are in a loop, if there are cell, then to calculate the EMF we have to take this rule, that is we have to consider the positive terminal of positive terminal of cell as a higher potential, negative terminal of cell at lower potential, and it should be independent of current. Here should current, the direction of current does not matter in here. Next point, current flows from higher potential to lower potential in a resistor. So current entering terminal of resistor is at higher potential and current leaving terminal is at lower potential. We have to consider it, that current flow from higher potential to lower potential, we know that in a resistor. So from above it is clear that so current entering terminal of resistor is at higher potential and current leaving terminal is at lower potential. This can be considered at, this is a cell, this is positive terminal and negative terminal. So this terminal will be at higher potential and this terminal will be at lower potential independent of current. Current may be in this direction or in this direction. Again in this here direction matters in a resistor, that is current entering terminal will be, that is at this point current is entering, so this terminal will be at higher potential and current leaving terminal will be lower potential. So in resistor, direction of current has current decide the potential of terminal of the resistor, but in cell it is independent of current direction. Now to solve problem, we have to fix one direction of current in a loop, either clockwise or anti-clockwise. We can take any direction, clockwise or anti-clockwise, and we have to fix it. And after fixing, we have not to change that direction to solve the problem. Now from these three rules, let's calculate value, apply these above whatever we have discussed in the rules. Let apply this on a circuit and clear our understanding. For example, it is given, it is a loop containing cell and resistor. There may be another element like capacitor, inductor, etc. But here only we are considering a loop with cell and resistor. Here we have this is resistance R1, this is a cell of EMF V1, again this is R2 resistance, and this is E2 cell and EMF V2, and this is R3 cell and this is R4 cell. Now to solve the problem, we have to take as we have clearly in the above rule we have discussed that first we fix the direction of current. In this case we have fixed the direction of current as anti-clockwise direction, that is current is flowing like this. We may fix in the clockwise direction also, so we have to choose only one direction. The answer will be same. So here first see, after fixing the anti-clockwise direction, what we get applying KVL. So here first, for example, moving along ABCDA, here we are moving in this direction, opposite to the current direction, and that is we move from A, start to move from A and going in this direction, and this, and finally come to the A, and then see what is the total potential difference in a loop. So here in this loop, current is flowing in this direction, and we are moving in this direction to see the potential difference. So first, our first element is here is cell, and now we are moving from this direction to this direction, and we know that it is independent. The EMF of potential is EMF is of cell is independent of the current direction. Only it depends on the positive terminal and negative. Here this is at positive terminal, and positive terminal is at higher potential and negative terminal is at lower potential. So potential difference, that is, if we go through this, so we have to take higher minus lower, lower minus higher, final is lower and initial is higher, so it should be negative. So we are written here minus E1, that is potential difference of this is minus E1. Again in resistor, because current is flowing in this direction, so this terminal is at a higher potential and this terminal is at lower potential, and now we are going from here to here, so final is this terminal and initial is this terminal. So final minus initial, if we say, the final is at higher and initial is at lower, so this will be potential difference across will be again positive. So and the potential difference is given by I into R1. We are considering that I current is flowing in this circuit. Again in this, again we are going from here to here. Our final is this terminal and lower initial point is at this point. So final minus initial is higher minus lower, so will be positive. So potential difference across this will be positive, I into R2, I4. Again at V, see that from here to here, we are going from here to here. This is final and this is initial point. So our final is at higher and initial is at lower. So potential difference across will be positive and given by I into R3. Again we are going at this, now from here to here we are going, crossing the cell 2. Now our final point is at this point and lower is at this point. So final minus initial, so higher minus lower will be positive, so E2 will be positive, here plus positive. Again in this, we are going from here to here, that is from lower to higher, or initial point to final point is our higher and initial point is at lower, so will be higher minus lower will be positive. So final I into R2 will be 0. This is equation 1. So we have firstly moved in the circuit like this. Now we can move in any direction. Firstly we have moved in the anti-clockwise direction. We should move in the clockwise direction. We have firstly moved in the clockwise direction. Let's move in the anti-clockwise direction and see what happens. Now in this loop we are moving like this, from A to D, D to C, C to B and B to A. So now again in this case, from we have started from A. This point is at initial and this is final. Our final is at lower and initial is at higher. So lower minus higher will be negative. So we can write minus I into R2. At this, final is lower and initial is higher, so lower minus higher will be negative, so minus E2. This will be potential across this will be minus E2, so minus E2. Again at this point, final point is at lower and initial point is at higher, so lower minus initial that is final minus initial, that is lower minus higher will be negative, so I into R3. Again same things, lower and higher, so minus I into R4 and minus I into R1. Again now at this point we are going in this direction. It is at higher, final point is at higher and lower point is at initial point is at lower, so higher minus lower will be positive, so plus E1 equal to 0. And now we have completed the loop. Again we see that minus multiplying by minus E1 plus IR1 plus IR4 plus IR3 plus IE2 plus IR2 equal to 0. So from 1 and 2 it is clear that we get the same result. So moving in any direction in a loop will give the same direction of same value of potential difference in the whole loop. That is, sum of all potential will be same. Sum of all potential difference will be same. It does not depend upon our movement.